So now knowing what we know about the basic graphs and that graph that we just saw, we actually can describe the appearances of these two graphs without ever having to graph them. Although, of course, we could graph them in Desmos if we wanted to. When r is equal to a constant, this is a circle. It has a radius of 12, and it is centered at the origin. Done. I mean, I can verify it in Desmos. There, you can see it. So I said r is equal to c, some constant. I set my c at 12, and so be it. I'm doing something a little bit fancier here because I am establishing that theta is less than or equal to b being this constant for this angle, and I put in that point, but you don't have to do that. You can just graph r equals 12 if you so desire. If I graph r equals 12, oop, there's r equals 23. You can see how this works. Turn that off. There you go. It's a circle. Lovely. All right, now what about r equals -6 theta? Well, we just saw r equals theta creates spirals. And so multiplying it by a constant isn't really going to change that. It's still going to be a spiral. It's a spiral that rotates counterclockwise but it's going to start off a little bit differently than the last one. So let me show you here. So I'm going to turn off the circle because we don't need the circle anymore. And then if I look at my angle, so the one we just did had a equal to 1. So it was r equals 1 theta. So when I graph that, it does this, right? No problem. So it started off here, back here, kind of swings through and goes around. Okay, but now if I go to -6, watch what'll happen. R equals -6. Oh, it zooms out a lot. So I got to zoom out to kind of capture it. So let me go back. And it goes around like that and goes through. So it's still rotating counterclockwise, but it's actually a lot more spread out as a spiral because it's being multiplied by 6. And it goes into quadrant 3 first instead of quadrant 1. It's starting down here in quadrant 3 and then kind of zooming around. So it's a spiral that has a lot of radial stretch. So counterclockwise starts in quadrant 3 and has a lot of stretch because you're multiplying by 6. All right, now let's take it up a notch and do a whole other graph that we have not seen before, something different. We're going to take r equals 2 minus 2 sine of theta. All right, well, let's start with some basic points. And I've given you a hint, which is to do multiples of pi over 6. So remember, pi over 6 gets you a lot of the unit circle because pi over 6 is right here, 2 pi over 6 is pi over 3, 3 pi over 6 is pi over 2, and so on. There's 4 pi over 6, 5 pi over 6, 6 over 6 makes pi. So if I start at 0, and let me get all my angles in. So pi over 6, pi over 3, that's 1 pi over 6, 2 pi over 6, 3 pi over 6 makes pi over 2, 4 pi over 6 makes, let's see, 2 pi over 3. There we go, 2 pi over 3. Then 5 pi over 6. Oh, this one was 2 pi over 6, if you want to know how this works. So some teachers actually teach you this technique for learning most of the angles. It doesn't get you the pi over 4s, but it gets you a lot of the angles of a unit circle. So some instructor might have taught you 0 here, pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 over 6. Here's 7 pi over 6. So 6 over 6 makes pi. Then 7 pi over 6, no problem. Then 8 pi over 6 is right here. 8 pi over 6 is 4 pi over 3, which is right down here. Then 9 pi over 6 is 3 pi over 2, which is right down here. Then 10 pi over 6 is 5 pi over 3, which is right here. So there's 6 over 6, 7 over 6, 8 over 6, 9 over 6, 10 over 6, 11 over 6, which is just 11 over 6. Sorry, that one doesn't reduce. I'll just kind of write that one. 11 pi over 6. And then 12 over 6. 12 pi over 6 is, of course, 2 pi. And then you keep going, right? There's 13 over 6 is back at pi over 6 again. And then 14 pi over 6 will be right back up here. Ooh, 13 pi over 6 didn't reduce. I might kind of write that over on the right. That's the way I've been doing those. 14 pi over 6, let's see, 2 goes into that 7, and then 3. And we'll just stop there, and if we need to go further, we will, but we'll stop. Okay, well, the first couple angles are no problem, right? So I'm putting them into this equation right here, because here's my polar equation right here. So I'm going to type 2 minus 2 sine of 0. So 2 minus 2 sine of 0, that would be 2 minus 0, which is 2. 2 minus 2 sine of pi over 6. The sine of pi over 6 is a half, so that's 2 minus 1, which is 1. And this is going to start getting crazy. So we don't want to do this by hand. This is not worth our time. So we are going to grab Desmos. So let me go to it. And I have this lovely table. I've actually turned off the points. I don't want the points, but I do want to give it all these values. And I can't put in theta and r. Desmos doesn't handle that well, so I still have to tell it x and y. I made sure that I'm in radian mode right here for the sake of the sine function. So I have to make sure I'm in radians. I'm sorry about that. So I typed in all my values. So 0, pi over 6, pi over 3, pi over 2, and so on and so on and so on. And then up here where it had a y1, I got rid of the y1 and I typed 2 minus 2 times the sine of x1. And to do that, I just typed x1. So if I type x and then the number 1 right after it, it knows that it wants x sub 1. And then you can see it's got all those lovely values. And that is the values, those are the values I need for my table, which is a lot better than me having to sit there and write them all out. So I'm going to use Desmos. So let me type or write all these numbers down to 268. Let's just do 27. We're graphing this by hand. We're not going to be able to go to that find a decimal place. And then 0, and then 0.28, and then 1, and then 2, and then 3, and so on. So I'm going to write all these down. And I want you to notice something else before I leave here. Which is why I didn't graph them. So I didn't graph them because if I graph them, Desmos thinks that I want the x, y coordinates. So it thinks this is an x and this is a y and this is rectangular. So it graphs this crazy thing which has nothing to do with our actual graph. So I turn that off because it's not at all what we want. That's not polar coordinates, which is what we need. So technically when we're looking at our table, this is a theta and this is an r value, but we can't get it to take it like that in Desmos. And just so I can prove it to you, I just paused it and I went in and typed it as theta, right? And then put this as 2 minus 2 sine of theta, and it still thinks it's x, y coordinates. It's not going to do it. Tables in Desmos are x and y coordinates. It doesn't know how to deal with our theta tables. So just turn off the graph. You don't need the graph part. What you need is the numbers part. And then we're going to go do the graph. All right, so I went one further down here. I went 5 pi over 2 for the heck of it. Why not? All right, so now we have to very carefully graph this spiral. So at the 0 axis, not 0 angle, right? It's a 0 angle, which is the polar axis, right? This part right here would be the positive polar axis, right? When theta is equal to 0. So, and theta is equal to 0, I want to be out at 2. So that's this part right here. Okay, now on the pi over 6 line right here, I want to be at 1, which is that second ring in there. So it's going 0.5, 1, 1.52 again. At pi over 3, I want to be at 0.28, which is not even to that first ring. That first ring is at 0.5. So I want to be in there somewhere. And then at pi over 2, I want to be at 0. So if you think of how this is curving, it's working like that. All right, now 2 pi over 3 is that radial line. I want to be back out at 0.28. And then at 5 pi over 6, which is this line, I want to be back out at 1. So 5 pi over 6, be out at 1. And then at pi, which is this line out here, I want to be at 2 again. So it's going like that. Okay, now at 4 pi over 3, oh no, sorry, at 7 pi over 6. 7 pi over 6 is this line. 7 pi over 6, I want to be out at the 3 ring. Here's 4, so 3 is right here. So I'm going to go out to there. I could go out to there right now. And then at 4 pi over 3, which is this radial line right here, I want to be at 4.73. Oh, no, 3.73, excuse me. So 3.73, which is, well, this is 3.5. That's 4, so it's kind of right there. And then at 3 pi over 2, I want to be down at 4. So if I want to swing this through, it goes like that. Now at 5 pi over 3, which is right here, I want to be at 3.73. So back to 3.73. So that's right there. And then at 11 pi over 6, I want to be back to 3, which is this ring right here. And back at 2 pi, I want to be back at 2. So it's going to kind of swing around like that. Now, I kept going a little bit just to show you, but at 13 pi over 6, 13 pi over 6 is this line again. It's back at 1. See, it's back where it was. And then at 7 pi over 3, which is this line right here, it's back at 0.28, which is where it was. And at 5 pi over 2, which is this line up here, it's back at 0. So it's actually cycling through the same picture over and over. This picture looks familiar. It looks like a heart, right? So it's called a cardioid. Cardi means heart in Latin, like cardiac arrest, right? If you have cardiac arrest, it means your heart, have a heart attack. So cardioid is like a heart shape, right? So it's a heart shape. And what's more, I noticed that the period of this heart shape is 2 pi. The period is kind of the theta angles that are needed to make one full circuit. Period doesn't quite mean in polar coordinates what it meant in other systems. So I'll make a little note down here. We'll talk about more about period in a couple pages, but the period in polar coordinates is the theta angles needed to make one full circuit, if possible. Some graphs do not have a period, like the spiral does not have a period because it just keeps spiraling out and out and out and further and further and further. There is no period for the spiral graph. But for the cardioid, there is. Let's look at it, shall we? Okay, so I do not want to graph that part, but I do want to graph the graph. So let me click that. And you can see, here, let me go back to 0. Starts at 2, right? And then as we swing through, there's 1, there's 0, it bounces back out, swings out to 4, and so on. And then everything from that point on just keeps swinging through, right? So it has a period of 2 pi. For every 2 pi radians, it just keeps cycling around over itself and creates another circuit. And it's a pretty shape.